have second derivatives of phi. So now these derivatives are going to be first derivatives of chi. These are standard techniques to reduce the order of differential equations, right? Okay. Now we do this expansion, and now finally this is our system. This is a system that we can work numerically. Okay. Of course, we can make it dimensionless. We can make it dimensionless as well, but I'm not going to show that now. I think it's sufficient. You see, this is a third. If we do this dimensionalization with make it dimensionless with omega and so on, we would end up with only two equations. It would be a two-dimensional dynamical system, right? And but already numerically you solve it, because v, you specify v as a function of phi, right? And then here you have the derivative, and then phi necessarily, we cannot get rid of phi. Why? Because phi will appear here. Remember that v is a function of phi. So once you state your potential, even if it's a Mexican hat, the Mexican hat potential or exponential potential or whatever scalar field potential you want, depending whether you're studying inflation of one type or another, or quintessence or whatever, you have to give a form for the potential, and that form will be a function of phi. So phi will appear, but doesn't matter because you have an evolution equation for phi, right? And then you have an evolution equation for h, and then this is the Klein-Gordon equation. So this is the system that you get with a scalar field, right? And so I think that I'm not now going to switch to the theoretical lessons. Any questions of what we've seen here?
D capital is the delimiter, right?
What?
Capital
D derivative.
That's derivative of phi, of v with respect to phi. Because remember that we declared v first as a function of time, which is a function of time because it's a composed function. Because v is a function of phi, and phi is a function of t. Therefore, v is a function of t. But I use this notation to specify that v is, strictly speaking, a function of phi. Okay? Any more questions on this? Wow, very bright people understood everything. These are standard techniques. You can do a lot of this by hand as well. You don't need Maple. In fact, GR tensor and Maple are good just for computing the tensors. Many times what I do is I get the slave to move the mountain to compute the tensors. And once I have the tensors, I pass them into a LaTeX file. Because Maple has a very nice feature that it can LaTeX its previous instructions. And then I print that and I work by hand. Sometimes it's more efficient. I do it by hand, and that's it. These are very standard procedures of manipulating ordinary differential equations. Just to show you this feature of Maple. Let's see this one. See. This is just to show you. So I tell Maple to LaTeX this, and voila, LaTeX. so similar to dust that we can treat them as dust. The same thing with perfect fluids. Now, let's go to see all these things here. This is the density, this is the isotropic pressure. This will be the anisotropic pressure, and this Q will be the energy flux. So let's see how they relate. We choose an observer. Always we choose a class of observers. As we know, is orthogonal to the 4 velocity. This is very important because this allows us to set coordinates. Whenever we speak of time, we are speaking of the proper time of these fundamental observers. Whenever we say space, we mean the three-dimensional hypersurfaces that are orthogonal to these world lines. And then we are safe. Somebody can say, relativity, it's all relative, it's all relative. Yeah, it's all relative, but that doesn't mean that everything is shaky. Once you define your observers, then your coordinates, time and space coordinates, are well defined. These coordinates, we call them comoving. And this is a comoving frame. See? Of course, if we have other observers, we can define a comoving frame with respect to these other observers. But then that comoving frame will not be comoving with respect to these ones. See? So we have to be careful which observers we are comoving with. Okay? Now, we align the coordinates. See? This is the nice thing. This is not the most general metric, but this is quite general still. And we have UA and HAB. And suppose this is a quite general metric. And given this metric, we can identify the 4 velocity will be something, will be a vector, time-like vector, whose only non-zero component will be the time component. This is UT. And then we can identify the coordinates of the space, of the space-like slices with the spatial coordinates. So time, proper time of comoving observers, space is the rest frame of these observers, right? So from now on, we're going to specialize on comoving coordinates, comoving frames. All coordinates we will see now, yeah?
Yeah, this last part is comoving frame alignment.
This?
This thing in the box.
Yeah?
One second, please.
Here? Yeah, this means that these are Kronecker deltas. That means that your H11 component will be the G11, the metric component G11. That's all.
Projection tensor.
Sorry?
Projection tensor.
Yes. Yes, what we're saying is that the coordinates of H are simply the space coordinates. See? That's it. That's all. See, that means that that objects that reside here will have 0 time component, and objects projected along these lines will have 0 space components. See? That's the whole meaning. We're choosing coordinates in a simple way. See? And it makes sense physically also. Is that clear? No questions here?
So ds square is the general frame.
Sorry?
The ds square, you have written in a general form.
Yeah, it's not the most general one, because see, in the most general one, this is valid only locally. See? The thing is, and I'll go back to this later. If you have rotation, then this is only possible locally, right? But we're not interested in rotating space-time, so in all space-times we're going to see this is true. Okay. In general, this is always possible locally, because when you have rotation, you don't have a global family of hypersurfaces that is always orthogonal to the 4 velocity. So for numerical purposes, you can always find, because of the vorticity, okay, because of the rotation. But in those cases, you define your rest frames, but they are not orthogonal to the 4 velocity. But you can still define rest frames. But I don't want to go into this complication because we will not need it in the course, okay? But you can say that this is the most general metric for any space-time whose fundamental observers have no vorticity. They're not rotating. Okay. Now, another question somewhere? Question? No? answered already? Energy momentum balance. Okay? This is, let's see it for the perfect fluid case. For the perfect fluid case, this is a vector. So it can be decomposed in its part parallel to the core velocity, and this is the energy balance. And this thing projected in the rest frames is the momentum balance. As you can see, here we have a dot, and there is a divergence of the core velocity, and there is a tilde here, which I'll explain soon, and then there is this fellow here with a dot here. And these equations, if you take this derivative and put the normalization condition of the four velocities and do these contractions, you get exactly these equations. In the previous case, for Friedman, Robertson, Walker, we only had this. Why? Because this and this are trivially zero for Friedman, Robertson, Walker models. Now, let's see what these things are. Here, whenever you see the dot, is simply the contraction of the covariant derivative with UA. And it's this thing here, and this is the four acceleration. You take the covariant derivative and you contract it with U, and this is called the four acceleration. In general, for all tensors, if you see a dot, it means that you take the covariant derivative and contract it with the four velocity. And this is the dot. Now this dot is called the convective derivative. It is the equivalent of a time derivative, right? Because remember that our time is, the direction of time is marked by the whirl lines of the observers. Therefore, any derivative that is projected in this direction is what we will think of as a time derivative. It's not the coordinate time derivative. It's not. First you take the covariant derivative of the object, and then you contract this with the four velocity. So it's a covariant derivative along the direction of the four velocity. We can call it the dot derivative, the convective derivative. Now, there are other things that appear here. This thing, tilde, the tilde is the contraction of the covariant derivative with the rest frames, right? In general, for all tensors, it's the same. However, here, you also have to contract the other index. Well, this is not correct, but anyway, I'll show you later the correct form. But the point is that whenever you see a tilde, it means you have to contract with H. And this is the equivalent of this, let's say we can call tilde nabla, is the transversal derivative. That is the derivative, but that is projected in the three directions of the rest frames, right? Of the hypersurfaces orthogonal. You take the covariant derivative and you project it in the direction orthogonal to the four velocity. And this is the equivalent to the spatial gradients. Again, in GR, time and space are relatives, are relative quantities. But since we already agreed that time direction will be the whirl lines of the fundamental observers, and the three space directions will be the three directions orthogonal to these whirl lines, then all what we do is to project the covariant derivative along the appropriate direction. And then we get convective derivatives and spatial gradients, right? Don't we agree on this? Everybody agrees? Everybody happy? Yes? Somebody not happy? Okay. Yeah. Einstein equations as a second order system. Let's see how Einstein equations look. This is a perfect fluid. This is our four velocity in a moving frame. This is completely general. Now let's take a general. Every space-time can be any metric, can be decomposed in this way: rotating, non-rotating, oscillating, complaining, whatever. All source, any metric can be put in this way. Okay? Now, let's see Einstein equations. See, Einstein equations now look like this. While this tensor is not symmetric, this means that this object is not exactly equal to this one, but it's very similar. So basically, this is like a symmetric tensor. There is no extra information writing the components here. Basically, independent components are this one. So what we have is this thing, all these things here, all of which are horrible algebraic combinations of second derivatives of the metric. Okay? So these are quite nasty equations in themselves. If I write them fully, I would take like 2 blackboards. And then this is equal to, we know that the energy momentum tensor in a comoving frame for a perfect fluid will always have this very simple form. So this is what we have to solve. Now, what does this mean? It means the following. We have 8 equations to solve. This equals 0, horrible constraint. This equals 0, horrible constraint. This equals 0, another horrible constraint. Now, these two are equal to the same. Therefore, they have to be equal to each other. Horrible constraint. This and this are equal to the same. Another horrible constraint. This and this are equal to the same. Another horrible constraint. Once we solve these constraints, we can use any one of these well, we still have this one, GTT equals minus rho, and then we can use one of these to get P. So we have 8 equations that we have to solve. Now we have 9 unknowns. We have a GTT, and then 6 of this one. Why only 6? Because we can always do coordinate transformations and we can eliminate 3 of them. And then we have rho and P. So we have 9 unknowns. The system is underdetermined, as it was with Friedman, Robertson, Walker. So with Friedman, Robertson, Walker were 2 equations, ordinary, and 3 unknowns. Here we have 8 and 9 in general. So you can see how gross, extremely simplification are the Friedman, Robertson, Walker models. See? Again, we're window shopping. I'm not saying we don't have to solve this. We need supercomputers to solve such a system in a general case. Okay, we need an equation of state of this form. Or, this is not the only form. Like I showed you the ideal gas. It's not an equation of state so simple as this one. But nevertheless, we need to impose a relation, normally an algebraic relation among these quantities in order to complete the system. And it depends on the physics of the system that we are studying. The choice of equation of state is not arbitrary. It depends on what we are studying. Okay? However, note the following. Einstein equations can also be closed So somebody tells me, don't waste time, just assign functions to the potentials. There I define an electric potential and the magnetic vector potential, and say, okay, fantastic, I have an electromagnetic field. But if you calculate the currents and the charges, it might be for you physical. So while it is possible to do this, it is not recommended. However, we don't have to be so black and white. Sometimes you do make some assumptions on the metric to simplify beforehand, okay, as I will show you. But these assumptions on the metric cannot be arbitrary. They must have some physical justification. We will see that.
Just can you elaborate a little bit about incomplete Einstein equation are always incomplete in the sense?
Yes.
In the sense for this you can say?
Well, they're incomplete because they have more unknowns than
Okay, yeah.
in that sense.
Okay, that's
They're always incomplete. You have to make assumptions. The assumptions can be physical, meaning an equation of state, or they can be geometrical or kinematic, or can be completely unjustified, arbitrary assumptions. Okay? But you have to make assumptions on that.
These are more unknown variables than equations,
Yes.
given equations. So you have to put some constraints so you will have equality between.
Yes, exactly.
Yeah.
Exactly. That's important. Now, there are four constraints that follow from the balance equations, but these constraints are integrability conditions for this one. Now, these constraints can always replace one of these equations. You can replace four of these equations with these constraints, and you can use them. But they bring no new information. They are integrability conditions, right? Just as in Friedman rollers and walkers, we saw it's the same, except that we have more complexity. And now, since Einstein equations are so horrible, we need to make assumptions, right? There are assumptions that are physical in the sense of the equation of state, but these assumptions, they close the system, but we can still have a very complicated system. Therefore, we're going to make other assumptions of a geometric nature, which are physically justified, and these are called symmetries. I'm going to define now what I mean by symmetries. Okay. Killing vector. It's not a vector that goes with a machine gun killing people. It's rather peaceful. Okay. There exists a vector we call psi, such that the lead derivative of the metric as the lead transport of chi of the metric along the direction of chi is zero. And this condition can be stated in terms of covariant derivatives in this way. There is any vector given a metric. Notice that here I'm not talking about observers. Any metric with respect to the observers will have a killing vector if it satisfies this condition. Right? If it satisfies this condition, then it's a killing vector. Now, if we select coordinates that align to the killing vector, then the derivative of the metric along this coordinate is zero. There is a killing vector. Anyway, Bianchi models admit a three-dimensional group of isometries, which are translations. See, a translation here, a translation there, a translation there. What space does it generate? R3, right? Okay. So this space-time, it has this group. It is the translations are a three-dimensional group whose orbits are also three-dimensional, right? So what? Okay, all this mathematical mumbo jumbo. What does it lead to? It leads to the following. Coordinates exist that align with the symmetry. What I mean by this that I can choose the coordinates aligning to the translations. Okay. One translation along the x-axis, so this will be my x coordinate. One translation along the y-axis, that's my y coordinate. One translation along the z-axis, that's my z coordinate, right? They don't have to be orthogonal, but it's very comfortable to be orthogonal. They just have to be linearly independent vectors. Now, if I do this, then the metric takes this form. This form of the metric is related to this choice, because having chosen coordinates like this, then the metric has to be the most general metric that is independent of x, y, and z. What is the most general metric that will be independent of x, y, and z? Is this one. Now, the time direction is not part of the symmetry group. You see? Only these are strictly space-like Killing vectors. Okay? So this is the most general metric that will comply with this symmetry requirement. Notice that the scale factors here are completely different one from the other. We have 3 scale factors here. Of course, you can tell me, well, why I can make coordinate transformations and then make this metric more complicated. Yeah, that's possible. But what we are saying, notice the statement. We are saying coordinates exist such that we get this. That doesn't mean that coordinates, you can have coordinates that will give a more complicated metric, but we ignore them. The statement is, given a Killing vector, coordinates exist that align with this Killing vector and make this coordinate ignorant. But that doesn't mean that you cannot, that is the only coordinate system possible for these models. It is the simplest one, but it's not the only possible one. But why should we bother with complicated coordinates if we have simple coordinates, right? That's the minimal action principle. Okay? So, now, once we have done this simplification of the metric, look at the effect of Einstein equations. From the horrible monstrous system that we looked before, we now have Einstein equations become a system of 3 non-trivial ordinary differential equations. Of these 4, only 3 are non-trivial. Consist of the algebraic combinations of these ones. Only 3 of them are non-trivial, right? There is one of them, one of these 3 can always be satisfied if the other 2 are satisfied. Okay. So we get, look, this is tractable, right? Do you agree?
Yeah, I have just one question, that here you are taking Lie derivative of GAB.
Yes.
And GAB is total in space-time. Means,
Yes.
okay, and these are the function of x, y, z, t.
Yes.
That means you are finding directions, 3 or more,
Yes.
that along which the Lie derivative of GAB is 0.
Yes.
And it means that, you have given the definition that you are dragging your space-time metric along this.
Yes.
But it doesn't mean that your GAB will remain constant as you are moving. But it means it will remain same.
Yes.
It will
remain the same. Yes. Yes.
while moving.
Yes.
That means not GAB but your dA square will remain same, no?
No, we're talking about not the Lie derivative is acting on a tensor, not on a scalar.
Yeah.
dA squared is a scalar.
Scalar, yeah.
No.
Yeah.
It's a metric. It's not the line element. It's the metric. The metric tensor.
Yeah, that's right. Yeah. So yeah.
Metric tensor.
Yeah.
Not the line element.
So okay. Yeah.
Okay? It's a tensor. It's the Lie transport of a tensor.
Tensor, yeah.
Not of a scalar.
Scalar, yeah.
Because the Lie derivative of a scalar is simply the ordinary derivative. Okay?
Yeah. No, so my question is that is the GAB will remain the
But
same along
no.
that transport, no?
Don't forget about this one. Look at this one. This is the condition that has to be satisfied.
Okay.
See? And where is the metric here? Well, the metric will be involved in the covariant derivative.
Yeah.
Okay? Covariant derivatives have derivatives of the metric. Okay?
Yeah.
So this is to illustrate the idea geometrically. You transport the metric along a given direction so that the metric remains fixed. The metric doesn't change. The metric is not constant. You're not assuming the metric to be a constant.
Yeah,
no.
Yeah,
the metric is a function.
Yeah, matrix is a function, yeah.
But you find some direction in which you can transport the metric along this direction. The metric stays put the same way it was, doesn't change. It doesn't mean it's a constant.
Yeah,
it's just that it doesn't change.
Yeah, doesn't change.
Okay, and this is equivalent to this condition. If this condition is met, then we select coordinates that align with this direction. And then we see that the metric will be independent of these coordinates. Okay? That's the point. Now, this can be that space-times may admit only one Killing vector. They may admit 2 Killing vectors, 3 Killing vectors. Minkowski space admits what? 15 Killing vectors. 10 Killing vectors. Okay? Freeman-Robertson-Walker models admit 6. Okay? Now, this system is, the energy balance takes this form. So this system, the existence of these 3 Killing vectors makes a huge simplification. This is a tractable problem, right? Now, what's the physical motivation? Well, physical motivation is that we have a space-time that, as we are going to see, this type of spacetimes are the so-called homogeneous, but anisotropic models. They are not physically, in nature you'll never find a Bianchi model, but they are very useful toy models. They're useful toy models, and then the assumption, see, the important thing is that the assumption that we use to simplify the metric is very well based mathematically. It's a group invariance, right? And so this means that maybe they're not very physical, these models, but nevertheless they are defined in a rigorous way, and as long as you remember that they are idealized models, what are they useful for? Well, sometimes, I don't know if you've heard, for example, people working on 2-dimensional gravity or 1-dimensional gravity. What's that? That's complete nonsense. Yeah, but it's a nice toy model. You can explore the effects on 1-dimensional gravity and see what happens. Or like what Sushant works in, black holes in 6 dimensions. What are you, science fiction?
Not 6 dimensions.
Not
in 6.
Not in 6?
D dimensions.
In D dimensions. That's a science fiction person. But it's useful.
Why? But the string theory demands higher dimension.
Yeah.
Law of theory demands higher dimension.
No, but that's the point I'm making. The fact is that there is a tendency of like in all sciences, there is always a conflict between the extreme pragmatists and the extreme theorists. So the extreme pragmatist comes and says, no, the world has 4 dimensions, everything is Newtonian. Observations, reality. Then the other one says, no, I want to fly high. I'm smoking pot. There's D dimensions and so on. And then there is a tension between them. But always there is a middle ground, right? There is a middle ground, and both extremes are necessary, because if we are only dreaming and so on, well, we need to touch ground occasionally. But all these pragmatists, they're also wrong. They're also wrong, and you have to fight them. You have to fight them with a hammer. Because, why? Suppose we go back in time. We are now in the 18th century. Newton's laws are very bar squared plus whatever, and then we don't want to be writing bar all the time, so we remove it. This is a trivial rescaling. So we can do this in the... Now, this is interesting because here you have a metric, you have a family of spacetimes, which is very similar to Bianchi. See, all metric functions depend on time. Yeah, all metric functions depend on time, but it's not Friedmann-Robertson walker. Like, for example, in the Bianchi 1 models, all functions depend on time, but there are three functions that depend on time. Here, two functions that depend on time. Friedmann-Robertson walker, one function. So these are quite simple models, are more general than FLRW. Now, field equations also simplify a lot. Here you have three, the GTT, the GRR, and the G theta theta. So these are the three equations that you have to solve, right? So, another example, FLRW models. It's a one-parameter family of models. Why one parameter? You remember the K0? K is a constant, a curvature constant. Okay? Remember the metric here. If you look at the metric, it's K0 is 0, minus 1, plus 1. Three cases. The same here, here. Here, three separate functions. So it's a three-parameter family of models. Models can be spatially flat, positively, the curvature of the three slices can be positive or negative. Okay, so now what are the symmetry groups? Well, the cosmological principle, as we discussed yesterday, requires that we have isotropy at every point, right? All our observations are isotropic, but at every single point, okay? Now, what we need is isotropy. What is isotropy? Isotropy is spherical symmetry, but around the center. See? All spherically symmetric spacetimes, you can choose a point which is called the center, or the fixed point of the group. If you make rotations, there is one point that is not affected by the rotations. Where is this point? The center, right? You can do all rotations you want, the center remains like this, doesn't care, right? This is a fixed point, right? So spherical symmetry means that things here are the same as things there, as long as it's a three-dimensional rotation, right? And things are the same in the same orbit, right? In every point of the orbit, things are the same. So for the fixed point, we'll see a completely isotropic world. It's a more physical example. Suppose you place yourselves on the center of a spherical explosion. Everything is exploding, buildings, mountains, everything goes away. But the explosion has to be spherically symmetric. And you are at the center. So you would see all buildings and mountains flying away in different directions at the same speed, right? Now, if you are riding in one of these buildings that is exploding, then you will not see an isotrope, right? It's clear. You would see that some objects are expanding further, faster than others, right? But if you are in the center, you see a completely isotropic explosion, right? So in a spherically symmetric models, there might exist a point in which everything is symmetric, right? There is a point, it's called the center. If you are an observer along the center, then galaxies, everything recedes from you at the same redshift, right? Now, in spherically symmetric models, there can be up to two places like this. We'll see that later. For the meantime, there is at least one point where things happen like this. Now, this doesn't satisfy the cosmological principle because it would be one observer, maybe two, but no more than two, for which this is true. For a cosmological principle, you need this to be satisfied everywhere. So why 6 killing vectors? Because you need 3 for the local isotropy, and you need other 3 to drag them along. Right? That's why you have 6 killing vectors. 1 is the local isotropy, but you want that to hold everywhere. So you have to drag this group along 3 dimensions, along killing vectors, right? See, 3 of the killing vectors are acting on the sphere that surrounds every point. And the other 3 killing vectors are acting along the rest frames, right? That's why you have 6. Okay? And local isotropy holds everywhere, so you have the 3 vectors of spherical symmetry, which define local isotropy, plus 3 killing vectors of either one of these Bianchi models, the 1, 5, or 9. These are the ones that, and this result was proven by Robertson and Walker, and it's unique. It's a unique result, and it defines the Friedman-Robertson-Walker models, which we have been already studying. Okay, so with all this tour around the store that sells appliances, we have seen how Einstein's equations really reduce to very tractable levels once we impose symmetries. Symmetries meaning actions of isometry groups. Okay, they are defined killing vectors, and they are Lie groups. Okay, so this is what people have been doing to solve. Of course, I will show you that there are some solutions. In fact, solutions that we will look afterwards, Sekker's solutions, they admit no killing vectors. So don't think that we can only do solutions that admit killing vectors, right? We can even work with solutions that do not admit killing vectors. But nevertheless, the idea is to show you how Einstein's equations become mathematically tractable once we impose group symmetry. Okay? Now, Module 8 directed wrong word, Lecture 4. Now. How much time I have?
Almost time over.
An hour?
Over.
Time is over. Over.
It's over. Okay, so I'll leave this for tomorrow.
But I have to make a couple of announcements before we discuss.
Okay, so we'll leave this for tomorrow.
Yeah. There are few things. One,